Good afternoon. Welcome to week 2 of this course on applied optics offered by NPTEL. I hope all of you have watched week 1 videos, and just for a reminder, the week 1 and week 2 assignments are due next week. So all of you should try and attempt the assignment problems this weekend itself, or maybe early next week. So for those of you who are joining for the first time, this is just a recap of what we discussed last time. We basically discussed the course logistics. So mainly, this course is a 12-week course, which is offered by NPTEL. And every week, there will be some lectures followed by a quiz of MCQ type questions, roughly about 10 questions. And these quizzes will be graded. And at the end of this 12-week course, you will also have one exam. So based on your marks in the quiz as well as the exam, you people will get a certificate and a grade. So every week, every Saturday from 3 p.m. to 5 p.m., we will be having these live sessions wherein I would be discussing some of the previous year's assignment problems for all of you, so that it helps you solve the current session's assignment problems. So the questions are quite similar, or at least of similar difficulty level between last year and this year. So hopefully solving the previous year's assignment problems will help you in doing well in your current semester. So that's that. And if you have any queries, you can use these 4 channels for doubt clearing. The first one is this live Zoom session. Every Saturday you will join over here. Second one is the course forum. Please actively use the course forum. The instructor and the TAs, all of us actively look at the course forum and try to answer as many questions as possible. So, and the third one is the YouTube channel. So that's the link to the YouTube channel. I have put it up in the chat box. So this is the YouTube channel where these sessions are live streamed. So if you happen to miss some session by chance, then you can definitely go to this YouTube channel and watch the previous week's videos. And I also upload some other concept based or some other physics based kind of videos on this YouTube channel, or programming based videos, programming in Python and Mathematica and all those kind of videos. So you may want to check out that YouTube channel. And if you subscribe to it, then you will get notification every time some new video is uploaded over there. And the fourth and final channel for doubt clarification is to send me an email. So I will try my best to address your queries, but you should follow this particular order for doubt clarification. First one is this live Zoom interaction. Second one is the course forum, which I highly encourage all of you to use actively. The third one is the YouTube channel. Again, please post your queries or concerns or comments actively over there. And the final channel, if none of these work, is to send me an email. Yeah, so this was what we did last time. And last time, we also discussed some 4 to 5 preliminary questions from week 0 assignment. So week 0 assignment is not graded. It is just a preliminary test to test your basics and to see where you stand currently and how you should go forward. So very basic questions. Light is, of course, an electromagnetic wave, and electromagnetic waves are transverse in nature. Transverse meaning oscillations of the oscillation is perpendicular to the propagation direction of the wave. Then in an electromagnetic wave propagating in an isotropic homogeneous medium, electric and magnetic field vectors are perpendicular to each other and also perpendicular to the direction of propagation. So, and then the fourth one, light wave exhibits both wave and particle nature. And finally, when light passes through a small aperture, then which is comparable to the wavelength of light, then light bends. This phenomenon is known as diffraction. So these were some preliminary questions we discussed in the last week, apart from the course logistics. And from today, we will start with week 1 and week 2 because both these assignments are due next week. I think 8th of August is the deadline. So all of you should definitely try and attempt these questions in the upcoming few days. So I hope we are ready to start with week 1. Are there some students who did not join in the last class? If so, please raise your hand. I see some familiar names and I do see some not so familiar names. Okay, I see Sadia. So, hi Sadia. Are you joining us for the first time? Hello?
Yes, ma'am.
Yeah, so hi Sadia. So last time we also had an introduction. Every student kind of introduced themselves. I introduced myself. So in case you don't know, I am Radhika Prasad and I am doing PhD in physics from IIT Kanpur. So Sadia, could you just briefly introduce yourself before we formally proceed with our week 1 questions?
Good afternoon, ma'am. This is Sadia Mahin Siddiqui, and I'm into a CSC course at OU, and I'm excited for this course.
Okay, so you are in which year?
I just joined the first semester.
Oh, you are a fresher. So you are in the first semester, okay. And this is which university?
Osmania University.
Osmania University, I see. And you have joined the computer science program over there, is that right?
Yes, ma'am.
So how come you got interested in physics and in particular optics?
Actually, ma'am, I prepared, I was thoroughly interested in physics, and I was on to join IIT like Monday or somewhere.
Haha.
But due to the travel restrictions, I just had to join somewhere in Hyderabad. So I just went there, but I really wanted to cope up with the studies there. So yeah, this is what brought me here.
Okay, very nice. By the way, Osmania University is also nice, so you need not feel that you are missing out on something by not joining IIT Mandi. You will definitely do well at Osmania University, I'm pretty sure. And of course, you can keep on taking NPTEL courses from various IITs and keep up your pursuits in physics. So great, good to have you, Sadia.
Thank you.
And are there any more new students? I see some new names. Let me see if my memory is sharp enough. Uh, Anita, were you there last time? I mean, I don't think so. Uh, Anita, are you there? Could you just unmute yourself? Anita and Abhi. I see these two new names. As well as Dr. Sheenu Gupta. So let's start. Abhi, are you here? Could you just unmute yourself, Abhi? Okay, I don't think so. Abhi is able to do so. Fine. Then I think Anita. Anita, are you there? Okay, fine. No issues. Dr. Sheenu Gupta. I think Dr. Sheenu Gupta has unmuted, but I don't think I'm able to hear. Hello? Hello? Can you hear me, Dr. Sheenu Gupta? I don't think I can hear you. Do you mind reconnecting, means leaving and rejoining? Or if that doesn't work, could you just type your brief intro in the chat box? Yeah, I would really like to know about all of you as much as possible, so that I come to know actually what level each one of you are. So last time I figured out that many of you are from this AET college. Uh, yeah, I had a whole bunch of students from AET college in third year. So that was the level. Then there was one student who just completed class 12. Then today we have someone from first year. So I just want to gauge the level. Then we had one high school teacher as well. So uh okay, fine. So Dr. Sheenu Gupta, you just want to refresh your optics basics, like that's very great. And it seems you are already in a position where I am actually aiming to be, because I'm pursuing my PhD. I'm yet to complete my PhD, and you have doctor in front of your name. So I believe you have already defended your PhD thesis, if I'm right. And yeah, great. So you are already in a position where or at least I am dreaming to be. Great. So you teach physics or some other subject, like is it physics only or mathematics or CS physics? Okay, great. So good to have you, Dr. Sheenu Gupta, and I hope to learn from you as well. So I'm not sure how much I can convey to you, but I definitely look forward to learning some things from you. Definitely how to defend a PhD thesis and how to uh, carry forward one's journey in PhD. Okay, so with that out of the way, let us finally begin. So, in week one, we were introduced to some of the basic concepts in optics, some very preliminary stuff like what is a wave equation and what are lenses, what kind of lenses we have, what is the lens formula, and so on and so forth. And in week two, we discussed more about this geometrical optics. Namely, we learned how to use the matrix method to basically analyze different kinds of configurations of lenses. So that's what we did in week one and week two. And we will now look at some of the questions. Okay, so let's get started. First question. A wave satisfies the relation psi x comma t equals to psi x plus minus lambda comma t, where the parameter lambda is, you need to select what lambda is from these options. So as always, let me just start the poll. So for each of these MCQ questions, I will launch a poll, and I would request all of you to participate in that poll and select the correct option. You would have a minute or two, and then after that, we will discuss the correct answer. So everyone, please take about a minute to answer. Okay, I see that many of you have answered, some of you have still not. So I request all of you, please try to attempt. It's okay if you get it wrong. I am here to tell you the correct answer. Okay, so let me stop the poll now and share the results of the poll. So it's quite a varied answer. A lot of you have selected all kinds of options. So let me now discuss the correct answer. So the correct answer is that lambda is known as the spatial period. Oh, wait, I need to activate my pen. Yeah, here the pen is. So yeah, so lambda is the spatial period of the wave, And what are the other terms? So what is the spatial period? Let me just draw it over here. So let's say this is my y-axis, this is my x-axis, and let me draw the wave for you. I hope my drawing skills are okay enough. Yeah, I think this looks like a sinusoid. So this is the x-axis, and this y-axis is where we are plotting this this function, this wave function. And this lambda parameter is the spatial period, meaning this length, which completes one period. So from here the wave oscillates, it goes up, then it comes down, it goes down again, and then finally comes back to its original position after one full cycle. So that is known as lambda, or the spatial period of the wave, also known as the wavelength of the wave. Okay. And what are the other terms? So the other terms, phase of the wave is the entire term kx minus omega t, which is there inside the sinusoid. So this wave function is basically given as sine kx minus omega t or cosine kx minus omega t. Either of the options will work. And this entire kx minus omega t is known as the phase of the wave. What is the temporal period of the wave? So temporal period of the wave is known as time period, which is nothing but 1 over the frequency of the wave. Okay. Uh, so that's that. And amplitude of the wave. Okay, so amplitude is the maximum displacement. So this distance right here is the amplitude of the wave, which comes as the prefix to this a sine kx minus omega t. So that's the amplitude. Yeah, so these are what the terms mean. I hope it is clear now. So we can proceed to the next question. Okay, so let's move ahead. Equation of a harmonic wave propagating along x-axis at t equal to 0 with amplitude 5 meters and wavelength 50 meters is what? We need to select the correct option. So I have already written the template form for a wave. It's right here, a sine kx minus omega t. So I believe you all should be able to get this one. So please take about some time to answer, then we will discuss. Okay, so nice. Most of you have answered. So let me discuss now. So most of you have got the correct answer. The correct answer is option A, y equals to 5 sine 2 pi x over 50. Now let me tell you why this is the correct answer. So the most general form for the wave would be A sine kx minus omega t plus maybe some initial phase, let's say some phi initial that is there. Now what we are given is that the wave is propagating along the x-axis. That's why we have this x over here. Had the wave been propagating along y-axis, we would have ky. Had it been propagating along the z-axis, it would have been kz. Along any other direction, let's say propagating along the r direction, we would have k dot r inside this sine term in the argument for the sine. But it's told that it is propagating along x-axis. That's why we have kx over here. Now, further, what information are we given? So typically the initial phase is 0, and also we are given that at t equal to 0, we are supposed to look at it. So that means we have y at t equal to 0 is a sine kx because t equal to 0. And further, we are also told that the amplitude is 5 meters. So amplitude is 5 meters, meaning this is equal to a. So we are told a equals 5 meters. And also we are told that wavelength is 50 meters. So wavelength, as I mentioned above, is nothing but lambda. So lambda equals 50 meters. And k, what is k? K is basically the wave vector. So there's a name for this k, which is called wave vector. Wave vector. And it's a vector, but the magnitude of it is this k. So this is nothing but 2 pi over lambda, where lambda is your wavelength. So putting all of these things together, we will get a is nothing but 5 meters. So 5 sine k is 2 pi by lambda. Lambda is 50. So 2 pi over 50 into x. So that's how we get option A. So I hope it is clear up until now. If at any point you have any questions, please feel free to stop me. Okay, so someone is asking me in chat box. Yeah, so if you have any question at any point of time, feel free to ask me by either unmuting yourself or by raising your hand or putting in the chat box. So someone is asking me, could you please tell which subject are you pursuing for your PhD? Okay, very nice, Lokesh. So Lokesh, are you joining for the first time? If that's the case, okay, let me introduce myself once again. So, hi Lokesh, I'm Radhika and I'm doing PhD in the Department of Physics at IIT Kanpur. And within physics, my field is quantum optics. So, in this course, you are basically studying what is typically known as classical optics. And what I do is study quantum optics, meaning I study how photons behave. So at the photon level, I try to investigate the properties of light. So yeah, if that helps, if that clarifies your query, Lokesh, fine. So I think we can move forward. Okay, so now we have a very simple question. Let me relaunch the poll. Okay, units of angular frequency omega is. We need to simply select the unit. This is quite a simple question. Yeah, you have a few more seconds. Okay, so let me stop the poll. So as expected, most of you got it right. But I'm still waiting for that one question which everyone gets right. So that's my dream, to see that by the end of this course, maybe at least all of you should get the answers right. So I will try my best to convey the knowledge that I have. Okay, so the correct answer for units of angular frequency omega is radians per second. Now, what is hertz? Hertz is the unit for frequency, not angular frequency. Note that there is a difference between frequency and angular frequency. So, hertz is nothing but it's basically 1 over second. Okay, and per second is basically hertz, but nobody says per second. It has a typical name, hertz, after the scientist Hertz. So meters per second is for velocity. And what's the relation between angular frequency and this normal frequency? So what we have is angular frequency omega is 2 pi times the regular frequency, typically denoted by mu. So this is the relation between angular frequency and the frequency. Okay, so let us proceed further. Let me launch the poll again, clear the results. Yeah, fine. Next question. If psi 1 and psi 2 represent two separate solutions of the wave equation, then psi 1 plus psi 2 is also a solution as per which particular principle? Principle of wave propagation, principle of interference, principle of superposition, or Huygens principle? Huygens or Huygens, I never get this guy's name right. So, yeah, it's a very difficult pronunciation for me. It's something like Huygens. So, I typically struggle a lot with trying to pronounce this name. So, he was a Dutch person. So, in Dutch, the pronunciation is somewhat complicated. So, Huygens is how I get it. Okay, so again, this is quite a simple question. Let me end the poll. And here are the results of the poll. So the correct option is options. Oh, let me change the color of my pen. I should go back to white. Yeah, so the correct option is principle of superposition. Now, why this principle of superposition is valid? So principle of superposition is valid for solutions of linear differential equations. So principle of superposition, this is valid for solutions of linear differential equations. Okay, and in optics we have what is called as the wave equation. Okay, so what is the wave equation? The wave equation is given like this. This is the 1D version, that's why x is there. So this is the wave equation. On the left hand side, we have derivative with respect to space. Because it is 1D, we are considering, that's why x direction. Then on the right hand side, we have derivative with respect to time. And how we relate this derivative with respect to space to the derivative with respect to time is through this term 1 over v squared, where v is the velocity of the wave. So this is the wave equation. All of you should have this on your fingertips. Okay, so that's the wave equation. And this wave equation is a second order homogeneous linear partial differential equation. Now, because it is linear, because of this linearity, we have the principle of superposition being valid. And since I mentioned Huygens, and since this is an option over here, let me just quickly state what is this Huygens principle for all of you. We will cover this later in this course when we move on to the wave description for light, wave optics. Right now we are in the classical optics domain where we are picturing light as rays. And after a week, next week onwards, we will start by treating light as a wave. So in that context, this Huygens principle will come into picture. But just to give you some perspective, let me state the Huygens principle for all of you over here. So the Huygens principle states that every point on a wave front is itself the source of spherical secondary wavelets and these secondary wavelets which emanate from different points mutually interfere. And finally, the sum of these spherical wavelets forms a new wavefront. So this is the Huygens principle. It helps us picture light as a wave, and we will discuss more about this in the upcoming weeks. So it's okay if you don't get all of this technical jargon right now, but what it typically means is that if you have a point source, let's say if there is a point source and it is emanating some spherical waves and it has a wave front, and each point on this wave front will then again give out spherical waves. So this point will also give out spherical waves. And then when you add up all these spherical waves, then you will get what is like, say, the resultant, the new wave front. So it's okay if this sounds all complicated. We will definitely discuss this in the upcoming lectures. Fine, so we can proceed further. Yeah. So speed of light, c equals to 3 into 10 to the power 8 meters per second in a medium of refractive index 1.5 is what? So when light travels in vacuum, it has a speed denoted by the constant c, which is 3 into 10 to the power 8 meters per second. And when it travels in some medium, then its speed changes. So that's the question over here. When it travels in a medium of a particular refractive index, what does its speed become? Okay, so I hope everyone has answered. Let me stop the poll. Okay, so again, most of you have got it right. The correct option is option B, which is 2 into 10 to the power 8 meters per second. Now, how do I get it? So, refractive index N, refractive index is denoted by N, is given as, okay, it's given as speed of light in vacuum divided by speed of light in the medium. So refractive index is basically the ratio of the speed of light in vacuum to that of the speed in the medium. From here, you can get that velocity of light in the medium is nothing but velocity in vacuum divided by refractive index. So this is C is 3 into 10 to the power 8 meters per second divided by refractive index is 1.5. So 3 over 1.5, that's 2 into 10 to the power 8 meters per second. Okay, great. So we can proceed further. So one of the important concepts discussed in the first week has been Fermat's principle. So this is a question on Fermat's principle, which asks, according to Fermat's principle, ray path would be only minimum, only maximum, extremum, or none of these. So take about a minute to answer.
Ma'am,
Yes, go ahead.
ma'am, I am Amborish ma'am. The derivation of Fermat principle, which I did in my first year BSc graduation. So there, I just from Olagatok book that from the least action principle, but I could not know the details of that least action principle. So which I read in my third year and also master's first semester. Is that the same thing for here applied? The least action principle. What is the action?
Yes, that's absolutely right. Least action principle and Fermat's principle are mathematically, conceptually the same, just that they are
Yes,
used
ma'am.
in different contexts. So that's
Yes,
why
ma'am.
you see these two different names, but you very rightly connected and very good that you are trying to draw these connections. So
Ma'am.
they are exactly mathematically the same. And apart from this, you can basically refer to any calculus of variations text, any book
Yes,
on
ma'am.
calculation of variations. So this particular topic of the principle of least action, which in optics people like to call it the Fermat's principle. So it's the same thing. And if you want to know, you could refer to any calculus of variations text.
Yes,
So
ma'am.
yeah, and if you want a very short, quick, and crisp introduction, then I remember last week someone was saying that they are interested in classical mechanics. So I recommended this book on classical mechanics by J.R. Taylor. Let me put it in the chat box. So
Yes, ma'am. J.R. Taylor.
yeah,
I have downloaded from last week.
yes. So that book by J.R. Taylor. Okay, wait, where did my chat box go? Yeah, so let me just put it down in the chat box. So this book by J.R. Taylor has one particular chapter as the introduction to calculus of variations. So you
Yes, ma'am.
can look at that chapter. It's a very short and sweet chapter, and that will give you a gist of this topic. Okay, so J.R. Taylor, classical mechanics, and somewhere towards the middle, I guess there is this chapter on least action, or the principle of least action, as people call it. So yeah,
Yes,
they are
ma'am.
the same.
Thank you, ma'am. Thank you.
Okay, so let us come back to this poll. Where did my poll go? Yeah, so let me stop the poll and let me share the results. Okay, great. So most of you have got this one right. So the correct option is extremum. So what does extremum mean? Extremum includes three things. It includes maximum, minimum, or stationary. So, and typically based on the physical situation, or based on the physics of the problem, you pick and choose whether you want to look at the maximum or the minimum or the stationary. But in general, the mathematics says that it should be an extremum path, and extremum includes maxima, minima, as well as stationary points. And as Ambarish recently just pointed out, that there is a concept called principle of least action. Now, what happens is mathematics says that it should be an extremum, but physics says that we should look for minimum. So when you are trying to find out stuff, you are typically interested in looking for minimum path, minimum action, least action. But according to mathematics, it can be either minimum, maximum, or stationary. So yeah, so that's what Fermat's principle states, that the ray path should be an extremum. Fine, so we can proceed further. Again, a simple question on refractive index and the speed of light. So let me relaunch. We just discussed a similar question over here. Uh, maybe just the question above. So let me just hide it. I hope you will remember it. We just looked at question number 5. So if you have been uh, attentively watching this, you would remember. Or if you lost track, no worries. We will revise it once again. Okay, so let me end this poll. Great. So again, so most of you are getting the answers right, and I'm happy with that. But I'll be the happiest when everyone gets it right. Okay, so let us come to this question. As I mentioned earlier, refractive index is nothing but the ratio of speed of light in vacuum, that is C, to the speed of light in the medium, denoted by V. So from this we get V, we know the speed of light in vacuum is 3 into 10 to the power 8 meters per second. We are given the speed of light in the medium as this 1.76 into 10 to the power 8 meters per second, which is nothing but 3 over 1.76. And if you do this, then this comes out approximately equal to 1.7. Okay, so roughly 1.7. So the correct answer is 1.70. We saw a similar question above, where we were given the refractive index and we were supposed to find out the speed of light. Here in this question, slightly different variation, slightly different form of it. Here we are given the speed of light in the medium, and we are told to find out the refractive index of the medium. So, but it's the same formula that is to be used. So this is the formula relating refractive index to the speed. Okay, so let me relaunch the poll. And typically, what medium will this be? 1.7 refractive index would be roughly the refractive index of ruby. So if you check the data sheets, then refractive index of ruby turns out to be of the order of 1.7. So ruby, yeah, rubies are red in color, so fine. So let's proceed to the next question. Okay, someone is having a concern. Calculation mistake from my side. No issues, no issues. As long as you understand the concept, that's very important. And please make sure that when you are attempting the quiz or the assignments or the exam, please make sure to double check your calculations, because you would be graded based on what option you have selected. So there you will not get a chance to justify that you did a calculation error or whatever. So please make sure, because it's an MCQ based assignment question wherein you don't have to show your calculations. When it is subjective, it is fine, because then you show the calculations, and as a result of that you do get partial marks. But when it is an objective question, please make sure to double check your calculations. Okay, ray path in a homogeneous medium is. Very simple question, no calculation involved. Just need to select the option. It's linear, parabolic, sinusoidal, or helical for a homogeneous medium. Okay, so let me end the poll. So the vast majority of you have got it right. The ray path is linear for a homogeneous medium. And if you have watched this week's videos, then you saw there was an example question of graded index fibers. Graded index fibers. What does graded index fiber means? That the refractive index of the medium is varying continuously. And by that, what do we mean? That refractive index is proportional to x squared. So refractive index changes with position. If this kind of a feature is there where refractive index is a function of the spatial location, then in this case the ray path comes out to be sinusoidal. It comes out to be sinusoidal. So yeah, so when it's a homogeneous medium, it is linear. Homogeneous medium, what do we mean by homogeneous medium? Homogeneous medium means that you have a constant refractive index. A constant refractive index. And how do we find out the ray path? The ray path we find out by Fermat's principle. as we looked at in one of the earlier questions. So Fermat's principle gives us the ray path. So using the Fermat's principle, we can find out the ray path. And how this is done? So Fermat's principle states that time taken by the path is extremum. So this means that delta integral over the path, that means change the variation in the path, n is the refractive index, ds is the path length, should be 0. So extremum, that's why it should be 0. So using the Fermat's principle, you can find out the ray path, and that gives us that in homogeneous medium, the ray path is linear. And if you have a graded index fiber where the refractive index varies parabolically as a function of x squared, then you get the ray path as sinusoidal function of position. Okay, so we can proceed. Last two questions for week 1, then we will move to week 2. Okay. So question number 9. A lens is said to be a thin lens when thickness is small compared to A, object, B, image distance, C, radius of curvature, D, all of these. So we typically we have looked at thin lenses and also one example on thick lens as well. So what do you mean by a thin lens? That's the question. Fine, let me stop the poll. So the correct answer is all of these. The thickness needs to be small compared to the object size, compared to the distances, compared to the radius of curvature. So then only it is called a thin lens. So all these basically thickness needs to be very small compared to all the other measurable distances in your system, in your optical system. Okay, so last question for week 1. Let me refresh the poll. So this is the last question for week 1. Then we will move to week 2 assignment questions. A double convex lens is made up of a material whose refractive index is 1.3. The lens is kept in a liquid of refractive index 1.46. It will behave as a converging lens or a diverging lens or a plain glass surface or none of the above. So take about a minute or slightly more to answer this question. This is the last question for week 1. So I want all of you to answer. Then we will proceed to the next week. Okay, so let me stop the poll. So the correct option for this is a diverging lens. And why so? Let us see. By the way, typical refractive index of glass is 1.3 and 1.46 is the typical refractive index for a liquid called carbon tetrachloride. So this is a compound, carbon tetrachloride, CCl4. Carbon tetrachloride is CCl4, and this happens to be a liquid which has the refractive index 1.46. Now, let us say we have a double convex lens and the medium outside the lens is N1, medium of the lens, refractive index of the medium of the lens is N2. When we have N2 greater than N1, then in this case, this double convex lens acts as a converging lens. Whereas, if N2 is less than N1, which is our case, we have N2 less than N1, then in that case, it is a diverging lens. Now, this is the case because in our case, we have N1 equals 1.46 and N2 equals 1.30. So, in this particular situation, the lens acts as a diverging lens. Similarly, if we have a double concave lens, so what's a double concave lens? A double concave lens looks somewhat like this. Again, medium refractive index of the medium outside is N1. Refractive index of the medium itself is N2. In this case, when we have N2 greater than N1, it is a diverging lens. Whereas when N2 is less than N1, then it behaves as a converging lens. And how do we get this, by the way? So if you recollect, then the relation between focal length and the refractive index is given as follows. So this is the relation. It relates the focal length to the refractive indices as well as radii of curvatures. And let us simplify this. Let us say that our R1 equals R2, mod of R1 equals mod of R2 equals R. In that case, you will get 1 over F is equals to plus minus N2 by N1 minus 1, 2 by R. This plus sign is for a double convex lens. You can check double convex lens. And minus sign is for double concave. And why so? Because for a double convex lens, you would have R1 equals R, whereas R2 equals minus of R. Okay? Because R1 is to the right side of the lens, R2 is to the left side of the lens, based on the sign convention. And similarly, for the double concave lens, you have R1 equals minus R and R2 equals R. So putting this thing into this equation for the focal length, you get this simplified form. And whenever focal length is greater than 0, we have a converging lens. And whenever focal length is less than 0, we have a diverging lens. So you can check from here based on the refractive indices and this whether it's a double convex or a double concave lens. So when you put in the proper sign denoting either double convex or double concave, as well as the proper number for these refractive indices N2 and N1, then you will come to know whether focal length is positive or negative. And if the focal length is positive, then it is converging. If the focal length is negative, then it is a diverging lens. So that is all for week 1. Let me wait for a few minutes and see if you have some questions up until now. So if you have any questions for week 0 and week 1, please stop me now and ask me before we proceed to week 2. So again, we have 10 questions from week 2. So if there are any questions, please ask right now. So is everything clear up until now? Let me just show you week 1 once again, so that if there is any point which is confusing, you can stop me. So we had some preliminary questions in week 0 about basic properties of electromagnetic waves. Then we had some simple questions based on refractive index, ray paths, and thin lenses. So that is all for week 1. It seems everything is clear to all of you and we can safely proceed to week 2. So for those of you who are joining late, here is the link to the YouTube channel where you will find out all these live streams as well as videos from the previous week and previous lectures. Okay, so I think we are ready to proceed to week 2. So here we go. So week 2 has been on discussing the matrix method in optics, how to use matrix to solve to basically figure out the ray path for simple optical configurations involving lenses and refractive media. So that's the focus for week 2. So we have the first question over here. Let me, as usual, start the poll. Okay, so matrix for refraction from a curved surface of radius of curvature r separating two media of refractive indices n1 and n2 is given by which of the following matrices? So please attempt it and then I will discuss the answer. Okay, so let me stop. So sadly, I see that very few people have got it right. So the correct option is option A. I think people got mixed up in the signs somewhere because a lot of people have selected option C. So let me do the derivation for you over here. So let's start with our derivation. We will derive this matrix. So let us say we have the principal axis. Let me draw the principal optic axis. Okay, that's the optic axis. Then we have the curved surface, refracting surface of radius of curvature r. And then we have a ray path. So let me draw the ray path. So we have a ray coming up over here, and then let's say, okay, let's say the ray follows this path inside the medium. So we have refractive index of the first medium as n1, for the second medium as the as n2, and the ray is going from here and it goes like this, and this is the optic axis. And let us now draw some normal and some angles. So this is the normal to the surface at this point, and the normal passes through the center of curvature. So this distance is the radius of curvature, which is r. And let's draw a horizontal line parallel to the optic axis. So this is a horizontal line parallel to the optic axis. And let us now denote some of these angles. So let's call this one as psi 1. Let's call this as alpha 1. And this whole thing right here, this entire angle right here, let's call it theta 1. Okay. And similarly on this side, let's call this one alpha 2. This whole thing is theta 2. And because we have drawn this line is horizontal or parallel to the optic axis, so this angle also is psi 1. Okay, so we have all these distances. And one more thing, let us label this point as P, and this distance, let us call it X. Okay, so I hope this diagram is clear to all of you. And if not, please feel free to stop me and ask. Okay, so now, according to Snell's law, so we have all studied Snell's law. What does Snell's law say? Snell's law of refraction says that n1 sine theta 1 equals n2 sine theta 2. 1 denotes the first medium, the medium in which the ray is incident, and 2 denotes the second medium, the medium in which the ray transmits after getting refracted. Okay, now we have what is known as the paraxial approximation. Now, what does paraxial approximation say? Paraxial approximation says that we will look at rays which are close to the optic axis, close to the principal optic axis. And what that means is that all the angles are small angles. So this is essentially a fancy way of saying that we will treat all the angles as small angles. So this means that sine theta is approximately equal to theta, which is approximately equal to tan theta. So that's what the paraxial approximation essentially says. Oh, sorry. So let's come back. So then from Snell's law, we have n1 sine theta 1. theta 1 is the angle of incidence from the normal, equals n2 sine theta 2. Theta 2 is the angle of incidence or angle of refraction from the normal. So this is Snell's law, and putting in the paraxial approximation, we replace sine theta just by theta. So we get this. Now from this geometry, we can see that theta 1 is nothing but psi 1 plus alpha 1. So let me just highlight it for you. Let me probably try to use some different color. So this is my theta 1 in red out here. So that's theta 1. And psi 1 is, let me use, let's say, blue color. This is psi 1. And finally alpha 1 is over here in white color. So clearly you can see that theta 1 is psi 1 plus alpha 1. And similarly, theta 2 is equal to psi 1 plus alpha 2. How? Again we will see. So psi 1, because this line is parallel to the optic axis, this is once again psi 1. And because this is parallel, again this angle is also equal to psi 1. So theta 2 is, theta 2, let me draw again in some other color, let's say green color. So theta 2, this green color is psi 1 in blue plus alpha 2 in white. So this is simple geometry. And also we have from this triangle out here, let me call this point O. So OPC is approximately a triangle, a right angled triangle, right angled triangle. Again, this is true only in the paraxial approximation with the right angle at O. So at O there is 90 degrees. So in that OPC, we see that tan of psi 1 equals x over r. And because of this paraxial approximation, we have tan theta approximately theta. So this is approximately equal to psi 1. So now let us put all these things together. Let us combine all of this. So we get n1, theta 1 is nothing but psi 1 plus alpha 1 equals n2 theta 2, and theta 2 is psi 1 plus alpha 2. So simplifying this, let us simplify this. We have n2 alpha 2 is approximately, let us take n2 alpha 2 to one side. This is approximately equal to n1 alpha 1 plus n1 minus n2 psi 1. Again, let us rewrite it, is approximately n1 alpha 1 minus of n2 minus n1. We will put in the value of psi 1, which is approximately x over r. Now we define the parameter called lambda. Note that this lambda is not the wavelength. This is just another parameter that we are defining. This we will define equals to n alpha, and p is another parameter that we define. It is called the power of the refracting surface. This we will denote by n2 minus n1 over r. Okay. So this parameter, typically lambda parameter over here, typically denotes the angle the ray makes with the horizontal, which is essentially the slope, the angle the ray makes with the axis, and p is refracting, is basically the refractive power. So using that, we will plug in over here. So this is lambda 2, this is lambda 1, and this term right here is my power p. So what we get? We get lambda 2 equals lambda 1 minus p times x. This is one equation we get. Then we see from this geometry again, what we will see is that height of the ray. So for the matrix method, we need two things. We need slope and we need height. So slope relation we already found out over here, and for height we will just discuss this. So height of the ray just before refraction is x1, and height of ray just after refraction, let it be x2. And what we see is that this will be the same. x2 equals x1 equals to x. What is x? X is this height of point, this OP distance over here in this diagram. So from these two, this gives us the height of the ray, this gives us the slopes of the ray, and from here we can formulate the matrix. So what we get, lambda 2 x2 slope and height is 1 minus p 0 1, and this is the input parameters. So this matrix right here, this which one I'm highlighting, is the matrix for this curved surface which is refracting in nature. So this is the matrix where P is given by this expression. So putting all these things together, we get the matrix as 1 minus P, meaning minus N2 minus N1 over R 0 1. So this is the matrix. So the correct option is option A that we have selected. So I hope this derivation is clear. So if there is any doubt, please ask me. It's a simple derivation, but it has quite a few steps involved in it. So confusion can arise in these steps as to what approximations we are taking, where we are applying those approximations, why are those approximations important. So from this, we see that this matrix method is valid only in the paraxial approximation. Otherwise, you will not be able to get this matrix. Okay, so it seems that people don't have any queries. Fine, let me proceed. Okay, I just discussed the answer to this question. So not realizing that there is a question based on it. So I hope this is that question which everyone gets right. So let's see. I have relaunched the poll. So matrix method is applicable for A, non-paraxial rays, B, paraxial rays, C, marginal rays, D, none of the above. And I just discussed the answer. Just now I said this. Yeah, someone has written in the chat box. So I request all of you, please answer in the poll itself. Please use the poll to answer the questions, not the chat box. Okay, so let me end the poll. Yeah, so I am somewhat sad because just now I said that this matrix method will work in this paraxial approximation. Over here, we just now discussed, and still it seems that many of you are selecting some other options. No worries. I hope that as time progresses, you will feel more comfortable and confident with these questions and will get the answers right. So the correct answer is option B, paraxial rays. Matrix method works only in the paraxial approximation, only in the paraxial approximation regime. And paraxial approximation means we are using paraxial rays. Okay. And some of you might have heard this term for the first time, marginal rays. So what is a marginal ray? Marginal ray is basically a ray which emanates from the optic axis, ray emanating from the optic axis to the edge of the aperture stop. Now, what do I mean by this? Let me draw a diagram to make it clearer. So we have a lens, and for those of you who might be interested in photography, I am. So you would have heard of this term called aperture. Aperture stop, f-stop it's called in photography. So anyway, so is there someone who indulges in photography? I guess these days everyone uses a smartphone to capture capture photographs. So almost everyone is some sort of a photographer. But is there someone who has a serious passion or hobby for photography? Could people raise their hand or write in the chat box if that is the case? Okay, nobody likes to click photos. Okay, how many of you use your smartphone to click photos other than selfies? Photos of some trees, some birds, flowers, stuff like that. Okay, it seems people are so bored, they just don't want to say anything. I understand. It's quite a boring lecture, it seems. Okay, some people are now coming out of their sleep and trying to answer. So I see Parth has said that he takes some photos. Madhu also takes some photos. Yeah, so in photography, there is a term called aperture stop or f-stop. What that means is whenever you do imaging with anything, with a camera or with a smartphone also has a lens in it. So imaging can only be done when you have a lens. So whenever you click any photo of any kind, remember that there is, oh, Ambarish also clicks photos, very nice. So remember, whenever you click any photo, there is a lens behind it. Okay, an image is captured only by a lens. Okay, Savia also clicks photos. Now I think people are waking up. Okay, it's good to see people waking up. So lens is the thing which captures the image, and you can block parts of the lens. Means you can select, you can block parts of the lens, and what you achieve by blocking parts of the lens, you reduce the intensity. So you reduce the intensity of light falling into your lens, and as a result, your image will be darker. So if you want to capture a darker image or image which has less light, you would want to block parts of your lens. How do you do that? You do that by changing the aperture, changing the f-stop number. So if you increase the f-stop number, then you basically block most parts of your lens and you have a, let's say, darker or dimmer image. So what that aperture is there, it's like a blocking metal sheet. So there is an aperture over here. You have a sheet which can move in and out. So this is a movable sheet, it's not a fixed thing. So as a result, you can block various parts of the lens. So you can block, let's say, this much part, or so let's say this much part will be blocked now. You will be blocking this much part of the lens. You are blocking this much part of the lens, and light can only go through this part. This can also change. Yeah, it restricts the field of view, you can say. It basically blocks your lens, and you can increase the aperture to cover the entire lens, or decrease the aperture to cover very tiny portion of the lens. And as a result, your intensity of the image changes. So if you have the aperture open to the maximum, meaning you will allow maximum light to enter the lens, and you will have a very bright picture. Sometimes it can be too bright if it is sunny. So if you are shooting in sun, you want to reduce the light that is entering. You don't want too much light so that everything becomes very white and too much bright. So then you would want to cover parts of the lens so that light falls through only a tiny portion in the center. So that will reduce the intensity, and it's a controllable thing. So right now we are blocking this much part, but we can change this thing, and we can basically say, okay, fine, I want to now block only this much part. So then we will be blocking, okay, I don't think I want to use purple I reserve for the rays, maybe blue. So I want to block this much part. Okay, so I'm blocking up to this part. Or you can say that I want to open up the entire lens and expose the entire lens to whatever light is coming in. Now, what is a marginal ray? So let me draw the optic axis first. So this is my optic axis, and a marginal ray is a ray which starts from the optic axis. So anywhere on the optic axis it will start, and it will go to the level where the aperture is blocking, up to that level. So the extreme point that is available, so whatever lens portion that the light can see, the ray going from the optic axis to that extreme point, this is a marginal ray. And of course, after refraction it will maybe go somewhere like this. So this ray is known as a marginal ray, which starts from the optic axis and goes to the edge of the aperture stop. Okay, so this is these are about paraxial and marginal rays. Paraxial rays means rays which make very small angle with respect to the optic axis. So a paraxial ray would be something like this, means very small angle with respect to the optic axis, like this. So this would be your paraxial ray. Okay. Okay, why I used the yellow color, I don't know. Typically, I reserve the yellow color for questions. Or maybe I should use the red color. So rays which make very small angle with the optic axis, these rays are known as paraxial rays. So I hope now paraxial and marginal are clear to all of you. Non-paraxial rays are rays which go all over the place. So meaning non-paraxial rays would be something like a ray which makes too much angle with the principal axis, something like this, non-paraxial. Of course, this I have drawn exaggeration, something like which goes to the tip of this lens, maybe too much angle. If your lens is really big, if the diameter of the aperture that is there it's too big, and you have rays which are making large angles with respect to the principal axis, then those are non-paraxial rays. Small angles means anything within 10 to 15 degrees, maybe about 20 degrees. So beyond that, if it makes 40 degrees, 50 degrees, then that is non-paraxial rays. Okay, great. So I'm happy people are asking questions. Fine. So that's that for paraxial rays. Let us proceed. Now we have some matrices. Okay, let me relaunch the poll. Okay, next question. The system matrix of optical system is given by the following matrix. Then focal length of the optical system is how many units? 4.2 units, 3 units, 6.2 units, or 5 units? So in week 2, we have discussed the matrix method, and extensively we have looked at a lot of examples which discuss this matrix method and how this matrix elements are related to the focal length of the system. So take about some time to calculate. I see a lot of you have still not answered the poll. Please do attempt the poll. It is for your own benefit. Okay, let me stop the poll now. Okay, so here are the results. And the results are a little bit surprising to me. It seems that many of you are not watching the lectures, it seems. I strongly recommend that people please watch the video lectures of the course. And even if you're not watching the video lectures, at least do download the lecture notes and have a look at the lecture notes. It will definitely help you a lot when it comes to scoring well in the assignments. Anyway, so the correct answer to this question over here is option A. Okay, let me get my white pen. Option A is the correct option. And how we get this? This is because the system matrix, the matrix for a given system, a system matrix is always a 2 cross 2 matrix because you have an input array which is of this form and an output array which is also of this form. So to relate the input array which is a 2 cross 1 array, it's a 2 cross 1 to another 2 cross 1 array, you need a system matrix which will be 2 cross 2 order, where lambda is the slope times the refractive index and x is the height of the ray. So a system matrix is in its general form given as follows. These are the elements of the system matrix. And what it tells you is that the output slope times refractive index and the output height, let's call this system matrix M, is M times the input parameters. Okay, that's the role of the system matrix. And that's how system matrices are important for us. Fine. So, does someone have a question? Suganti, you have a question? Okay, if not, then please keep yourself on mute. Yeah, so this is the system matrix, and how are these matrix elements related to the focal length? What we have is this element right here is super important element uh, in terms of the focal length. Why? Because minus A12 is equal to 1 over F. Okay, so from here we find out that F is minus of 1 over A1 by 2, and A1 by 2 we know it's this term right here. It's minus 1 over minus 0.240, which is 1 over 0.240, which is approximately equal to 4.1667 units. So we can approximate that to 4.2 units. Why units? Because we are not specified whether this is in centimeters or millimeters. So that's why units. So that's how the correct answer we get. So people, please remember this. This is very important. This relating the focal length to the matrix element, this is a very important relation, and you will definitely get questions based on this. Okay, so now we move forward. So actually we have 10 questions, but I see that I don't think I will be able to complete all of them in the given amount of time. So maybe let us solve question 4, and then the remaining questions I will cover in the next class, if that is fine with all of you. And in the meantime, I can upload these notes so you all can have a look at it. Okay, let me stop the poll. Okay, question 4 is pretty long. Let me see if there is a simpler, shorter question which we can answer. Uh, so before coming to the class, I always practice and solve, and you can see that I've left so much space for question 4 because it takes about that much space to solve this question. But maybe I think we can solve question number 6. This is a little bit shorter question and won't take about as much time. And since we have less time left, I think we will solve question 6 and then solve the remaining questions later on. Okay, so I'm sorry for skipping question 4 and 5 right now. We will definitely come back to it in the next lecture. But right now, let us look at question number 6. So let me relaunch the poll. Okay, so that's great. So we have this question: a convex refracting surface of radius 5 centimeters separates a medium of refractive index 1.33 on the right side from air on its left side. The refraction matrix for the above system is what? So we just looked at some refraction matrices in some of the earlier questions. So you can refer to those earlier questions. So everyone, please try to attempt the question. All of you should try to solve the question before I discuss the answer. That way you will have some idea as to what difficulties you are facing. And if you get the answer wrong, you will understand what issues you are facing and how to resolve those issues. Yeah, I see some people are answering in the chat box. So very good. I'm happy that you are trying to attempt an answer. But please try to answer in the poll. I have specially created this poll for all of you. So that you can answer in this poll. So this poll feature is there in Zoom and in the pro licenses of the Zoom. So yeah, I have purchased this pro license especially for this class. So please make maximum use of this poll feature. It is for your own benefit. Okay, so let me now stop the poll and discuss the solution. Okay, wait, let me share the results of the poll as well. Okay, yeah. So here are the results of the poll, and I'm very happy most of you are following, it seems, and most of you have got the answer right. So initially, first question, a lot of people got wrong, but after learning it, I see that people are picking up things quite fast, and now you have got it right. So the correct option is option B, and the matrix for a refracting surface, convex refracting surface or concave refracting surface for that matter, is for any refracting surface. So not just convex matrix for the convex for just the refracting surface is given as follows. These are the elements where P is your power of refracting surface given as follows. So P is called power of refracting surface. R is the radius of curvature, which is 5 centimeters. So this 5 centimeters is nothing but R for us. And refractive index is given 1.33 to the right side of the surface. Meaning what we have over here as our setup is we have this optic axis, then we have a refracting surface, and to the right side of this medium N2 we have, which is 1.33, and to the left side we have N1, which is air. So air we typically take approximately 1. So vacuum is 1, but air is also very close to 1. It's not exactly 1, but for all kinds of practical purposes, we can take the refractive index of the of air as well to be equal to 1. And the ray comes from here, and then it will refract and go somewhat like this. So this is the setup, and these are the values. This is my curved refracting surface over here, and this is the corresponding matrix for it. So now we can just plug in these values. So what are these values? N2 is 1.33. Again, this is typical for glass. So refractive index 1.3, 1.33 is roughly the typical value for glass, and this is air. So 1.33 N2 minus N1, which is 1, divided by 5, which is the radius. So this is nothing but 0.33 over 5, which is equal to 0.066. This is the value of P. So finally, we get this matrix as 1 minus 0.066, 0, and 1. So the correct answer is option B. many a times people make this mistake of the sign. So note that this sign is very important. This minus sign right here, this is very important. Many a times students miss out on this minus sign, and also the order, that it is n2 minus n1. So if you change the sign, or if you flip n1 n2 order, then chances are you will get the incorrect answer. Of course, if you flip the sign of p as well as the order of n1 n2, then you are consistent. But please note this sign that is used over here. And if we go to the previous questions, here we had actually derived this particular system matrix, and this little bit involved and long derivation out here. From this derivation, we had figured out the matrix for refraction from any kind of curved surface of some radius of curvature r, which is separated by refractive in which involves two media, refractive index n1 on one side, refractive index n2 on the other side of the refracting surface. So here, just to recollect, this is how we had derived this expression for the matrix of the refraction from a curved surface. And typically, this is the kind of procedure you follow to find out the matrix for any kind of system, whether it is a reflection, refraction, transmission, any kind of those systems. This kind of procedure you will follow, and this matrix basically relates the input parameters lambda 1 and x1 to the, so this is input side and this is the output side. So input side means where the ray is incident. So the ray is coming, it is incident on a surface, then there is some particular medium, some refracting surface, some lens, or some medium, whatever, and then the ray goes outward after refraction. So that is the output. So this is how these terms are related, where lambda is refractive index times the slope and x is the height of the ray. So I hope this part is clear, and let's come back to this question. Yeah, I hope now all of you understand why this is the correct option. And yeah, so that's all for today, unless of course if you people have some doubts. So there are a few more questions left in this session for this particular week. So as you can see, we have solved question number 1, we have solved question number 2, we have solved question number 3 as well. And then after that, we took some jump and solved question number 6. So we are left with 4, 5, 7, 8, 9 and 10. So we are left with 6 questions for week 2, which we will look at in the next week. So yeah, does anyone have any doubt or question up until now? Okay, so if not, let me just reiterate myself. So every Saturday we have these sessions, every Saturday from 3 p.m. to 5 p.m. It's a 2-hour session, and it will be on this particular Zoom link all throughout the 12 weeks of the course. 2 weeks are over. We had week 1 last time, and if you missed week 1, so if you happen to miss week 1, you can watch the video for week 1 on this particular YouTube channel, and I have just put up the YouTube channel in the chat box. So all the subsequent weeks, all the videos and all the lectures for the upcoming weeks, they will be available for all of you on that YouTube channel. And this live session will also be live streamed on the YouTube channel. So sometimes what has happened, I have noticed in some of the previous courses, it's because all of you join from all different places in the country. So sometimes the network does not support so well. So sometimes some students have faced issues in Zoom. So when they log into Zoom, they see things freezing, things not working out, things appearing blurred. So some students face these kind of issues, audio is not coming. In that situation, I would recommend that you definitely go to this YouTube channel and watch the live stream on the YouTube channel. On YouTube, the quality of the audio and the video is fantastic because it is from my network. I am uploading it, so I take care to upload it on a good network. So yeah, if any of you at any point of time face any issues inside Zoom, feel free to watch the YouTube live stream as well. Okay, so that is all from my side for today. If any of you have any question, please ask me. Else, we will meet next Saturday. So that's all from my side for this session. Yeah, so people can leave the meeting if they do not have any thing to ask or anything to say or any comment. So by the way, your week 1 assignment is due next week. Please do attempt the assignment. And please do watch the lectures. And for any doubts or queries, use the course forum or the YouTube channel. Yeah, thank you everyone. Thank you. And see you in the next class. Yeah, thanks all. So yeah, people can leave the meeting. The session is over from my end. Yeah, all of you feel free to leave the Zoom meeting, unless of course if you have any queries. Yeah, thank you. Yeah, I still see a lot of people in the meeting. So students, do you have some doubt? If not, you can, ma'am, suggest basic book of quantum optics, coherent state, etc. Okay, very good question, Ambarish. So, and since I'm studying this field, I'm doing PhD over here, I think I can suggest you some really good books. So, if you want to just get into the basics and understand things from a very elementary level, then there is a book on quantum optics by Mark Fox. So I'll put it up in the chat box. So Mark Fox quantum optics book is there. This is a very good book for elementary level. I think I have a copy of it. Let me just show you. So here is the book. This is how the book cover looks like. It's called Quantum Optics: An Introduction by Mark Fox. This is one book that you should have. And then there is a very standard text called optical coherence and quantum optics. And quantum optics, I also have that book. I'll show it to you. This is by Mandel and Wolf. So this book is there. It's quite a thick book. Let me just show it to you. It's pretty heavy. So this is the book. You can see the thickness of this book. But this is a very thorough book. It has basically anything and everything that you would ever want to learn about coherence and quantum optics. And this is quite rigorous. So this second book that I have mentioned by Mandel and Wolf, this is a very mathematically rigorous kind of a book. So you need to sit down with and solve the equations and all those derivations and do them in a much more rigorous manner. The first book that I said by Mark Fox, that is more on a slightly lighter side. It of course has all the details and the maths, but it is a little bit on an elementary level, and maybe you can start off with that book by Mark Fox. Then there are other books by Scully and Zuberi. You can have a look at this. They also have a quantum optics book. You can have a look at that as well. So these are some of the books on quantum optics that you can have a look at. So Scully and Zuberi typically falls, let's say, somewhere between Mark Fox and Mandel and Wolf.
Okay, ma'am. Okay, ma'am.
Yeah.
Since I previously yesterday I talk about the my interest to go in PhD in physical astronomy astrophysics, and also my also and interest in quantum optics and
Haha.
entanglement experiments. So accordingly, I have to prepare myself.
Yes,
So
yes.
I have asked for that.
Yeah. Then there's another book, Jerry and Knight. That is also of the same level as Scully and Zuberi. So you can maybe look at these kind of books. So I would suggest maybe you start off with Mark Fox. As you build up the concepts, you can move to Scully and Zuberi and Jerry and Knight, and side by side you can start off with this Mandel and Wolf. Mandel and Wolf is a really thorough and rigorous book. So Wolf over here is the Emil Wolf, who was the student of Max Born. So big guy. And this Wolf is the same Wolf. If you have ever heard of this book, Optics by Born and Wolf. So Born and Wolf is a very standard text on classical optics. So yeah, Born and Wolf is the standard gold standard for all things classical optics, and Mandel and Wolf is the gold standard for all things quantum optics. Okay.
Ma'am,
Yeah.
I have one query. Could I ask?
Yes, sure.
Ma'am, since I do not give any viva before,
Mhm.
so after I when I'm going to a viva boards, professors, what about the thing of professors? What about the questions I have to face, like the concept thought, like this period of I will also face in my.
Okay, so you are planning to give what kind of interviews, like a PhD interview you are thinking?
Yes, ma'am. PhD interview.
PhD interview. Okay, so typically how PhD interviews go about is that they will ask you your favorite subjects. Okay, they will not just randomly start bombarding you with questions all over the world. So they will first ask you your favorite subjects. So let us say you say something about my favorite subject is thermodynamics. So once you say thermodynamics, then they will start asking, okay, so can you draw the Carnot cycle? Can you explain what the Carnot engine is? Can you tell us how this heat transfer is working? So if you have different temperatures at different ends of the rod, how the heat transfer will happen? Can you explain heat transfer through some membrane or something, or stuff like that? Okay, and then they will build upon the questions. So let's say they start, okay, draw the Carnot cycle. You draw it, then they will ask you, please explain what the engine is, please explain how things are working in this, what the applications of this can be. As you mentioned, you said astrophysics. then I don't know much about astrophysics, but once you say astrophysics, they can ask you, okay, what in that astrophysics that you like, then maybe they can start off with some questions. So maybe they can ask you, okay, fine, can you explain about the Chandrasekhar limit, what that is and what that governs, and things around that. So all those things they will ask with simpler questions. They will start with based on what you said, and then they will build upon the difficulty of that level. Then they will try to broaden or diversify. So let's say you said astrophysics, they ask you some questions on astrophysics, then in between maybe they will ask you some mathematical question, let's say some stuff from mathematical physics, something about gradients, let's say some simple stuff. Then they will try to see that, okay, astrophysics, can you talk something about, let's say, quantum mechanics, and how you want to relate quantum mechanics with astrophysics. Can you answer some questions on quantum mechanics? They will ask you. Then you will say, no, maybe I'm not comfortable. Then they will not ask you. But if you say yes, of course, then they will start in a different direction as well. So it mostly this is like a scenario that I'm telling you. But of course, some people can be in a mode to grill the student and derive some sort of satisfaction by grilling the student. So people can be in that mode as well, and they will just ask you questions left, right, and center, and try to make you cry and feel miserable about yourself. There can be those people also. And if there are people like them, maybe that's a sign that you should avoid them as your potential supervisor, and you should maybe run away from that place. It's better. So yeah, that is a red flag from their end, and you should identify if they are trying to misbehave with you, in a sense that they are just trying to grill you for the sake of grilling and not trying to motivate you to answer the questions. So yeah, typically it goes like this, but of course there can be different variations in this, and there will be like 3 or 4 faculty members from different fields who will be experts in their fields. So they will ask, all of them will try to ask some questions and try to extract how much you know and how much you can learn on the spot. Maybe let's say you get stuck and they are trying to help you and guide you through some steps. Are you able to pick up those steps and immediately formulate some sort of a result? Yeah, that's the thing.
So actually, I have to prepare myself accordingly. That so
Yeah, you
I-
should typically select 2 or 3 strong subjects of yours. Don't try to cover everything. This is not a net exam or a gate exam or a jest or jam where you cover every subject. Okay, this is more of a PhD interview. So here they do expect you that you have some idea of some field that you want to explore. Maybe you are not fully sure as to whether you will continue in that or not, or maybe you are not fully sure within that what you want to do. But let's say you have something which interests you. So based on that field and a few related fields, you should prepare yourself. So don't try to cover 10 different topics. Let's say I want to do solid state physics, thermodynamics, quantum mechanics, optics,
don't,
astro, nuclear.
I'm not suitable in college matter itself.
Yeah, so if you're not suitable in condensed matter, then you need to tell that no, my interests are in astrophysics, in quantum mechanics, in optics. You can ask me questions related to these topics. And no, I'm not so much interested in solid state physics, condensed matter physics. So that's what. But you can't just say I want to do only I want to only work on this specific topic in astrophysics. I want to study only this particular galaxy. You ask me only about this galaxy. That will not happen. That will not work. You need to have some field in mind. At the same time, you need to be aware of other things, other related stuff as well.
Okay, ma'am. Okay, ma'am.
Yeah.
Okay.
Okay.
Thank you, ma'am.
Yeah. All the
Thank
best.
you. Thank you, ma'am. Ma'am, could I leave now?
Yeah. Sure.
Thank you.
Okay. Bye bye.